This presentation will focus on performing calculations involving solutions. Our learning targets today include using the molarity and dilution equations to solve problems and also performing solution stoichiometry. Let's begin by understanding the term molarity. Molarity is one way to determine the concentration of a solution. These two terms are often used synonymously. The way to calculate molarity is to use the equation molarity used to symbolize moles of solute over liters of solution and represented by a capital M is the equation that we will be using. We're going to focus on cobalt 2 chloride as the solute in the problems that will follow. And specifically, we'll be focusing on cobalt 2 chloride in its anhydrous form. So that means that the water that is in the hydrated form of cobalt 2 chloride has been evaporated or removed from the salt. It is important to distinguish between the anhydrous version and the hydrated salt because in performing calculations involving moles or molarity and converting to mass, we would have to incorporate the mass of water if we were using the hydrated salt. So for every mole of cobalt 2 chloride in the hydrated salt, there are 6 moles of water associated with that substance. Now, to eliminate the additional step of having to add the mass in of the water, we are going to simply use the anhydrous version in our calculations. The anhydrous version appears to be a light blue or lavender periwinkle color in the appearance of the solid. When it is added to water, it appears red or a magenta color in solution. So just keep that in mind as we are going through the problems and you notice the different colors in the pictures. Here are some examples of how concentration or molarity might be expressed on labels for injectables used in the medical industry. So here on this label, you'll notice sodium lactate present in a concentration of 0.167 molar in this injectable. On this label of the saline solution IV bag, you'll notice that the contents are listed as 500 milliliters of the solution containing 4.5 grams of sodium chloride. It's also noted here in millimoles per 500 milliliters. So for each 500 milliliters, we have 75 millimoles of sodium. So these are just examples of how concentrations of solutes are indicated in a solution. This table is from a report published in 2015 highlighting the sometimes life-threatening consequences from a failure to understand molarity and dilution calculations of concentrated substances such as glacial acetic acid. You might recognize acetic acid as vinegar. Well, vinegar is a diluted solution of acetic acid to about a 5% concentration. Glacial acetic acid is a dangerous chemical, mostly because it's anhydrous and extremely concentrated. The amount of water present is usually less than 1%, so it's very close to its purest form and as a result very corrosive. The report published here shows how glacial acetic acid has been associated with several adverse drug effects involving patients. When it's diluted to the proper concentration, acetic acid solutions have many uses, including medical uses. Unfortunately, due to individuals failing to understand differences in concentration and how calculations involving concentration are performed, the improper dilution of substances like glacial acetic acid can result and has resulted in severe injury and harm to the patient. So you can see in this first part of the table, circled here, the intended strength that was supposed to be dispensed to these patients here was 0.25%, 0.5%, and 0.49%. But what was actually dispensed to this patient was 10%, 50%, and 47% glacial acetic acid. So you can see in these cases, these last two here, the amount dispensed was 10 times higher than what should have been dispensed. And this resulted in injuries to the patient. So they might have walked in with a bladder infection or seeking treatment for a wound, and instead of being treated and healed, they walked out with increased bladder tissue damage and second and third degree burns. And then in these instances, in the second part of the table, you can see that the strength intended for the patient was supposed to be 5% or 10%, but in these cases, 99.5% was administered. So that is significantly higher. That's actually the glacial acetic acid in its purest state here being dispensed, and this has resulted in severe skin burns for these patients, permanent scarring, skin discoloration, and burns so serious that they require skin grafts. So we can see clear evidence here demonstrating how critical it is to understand how to properly calculate concentrations. Let's go over some practice problems and see if we can understand what proper calculation of molarity looks like. So remember, we'll be using the equation molarity equals moles over solute to solve these problems. Starting with example 1, we're asked for the concentration, remember that's synonymous with molarity, of a solution that can be made with 3 moles of cobalt 2 chloride and 0.250 liters of water. So this is the simplest type of molarity problem because all it requires is plugging in the numbers to the equation given above. Once you divide those values, you will end up with a concentration of 12.0 molar cobalt 2 chloride. Now remember, what this represents is the 3 moles of cobalt 2 chloride in its anhydrous form added to 0.250 liters of water to produce a solution of 12.0 molar concentration. Our next example has us calculating the moles of solute this time. So instead of calculating the molarity of the solution, we're looking for how much solute to add to 0.5 liters of solution to give us a 3.5 molar solution of cobalt 2 chloride. So here, note that we are solving for moles. Okay, we are given the other 2 variables. If you were to solve this algebraically, I think you can see that all you have to do is multiply both sides by 0.500 liters to get the answer. We are going to approach this problem solving from a different angle. Notice that 3.5 molar can also be written as 3.5 moles per liter. This is useful to know because as a result of being able to write the concentration this way, you can use molarity as a conversion factor in a dimensional analysis setup. So to solve using dimensional analysis, we will begin with our given value of the volume. So 0.500 liters is what's given to us, and we will incorporate now the molarity as our conversion factor. So when we insert the conversion factor, note that we will need to put liters at the bottom of the dimensional analysis table so that we cancel out the liters. So when we insert the molarity conversion factor, this is how it will look. Okay. Now note that you can cancel the liters and simply multiply the numbers at the top to get 1.75 moles of cobalt 2 chloride. So that tells you the amount of solute you will need to produce the 3.5 molar solution. Before we look at our next example, let's take a look at another strategy to solve molarity problems. So this strategy will involve the use of this diagram. At the top of the triangle, we have moles of solute, and at the bottom of the triangle, we have molarity and liters of solution. So these variables are the same as the variables in the original equation. To use this triangle, you must remember that moles of solute go at the top of the triangle. Now, when asked to find molarity, given mass or moles, the way to do that is you cover up what you're asked for. So I would cover up the molarity, and what you're left with in the triangle is moles over liters. So you're just dividing moles over liters, just like in the equation. When asked to find moles, given molarity and liters, this time you cover up the moles. Notice you're left with molarity and liters right next to each other. So when that happens, you simply multiply molarity times liters to get your moles. Finally, when asked to solve for liters or volume, the remaining variable, you would cover up the liters, and what you're left with is moles over molarity. So all you would do is divide these two values. Now, I would encourage you to use the triangle as a way to check your work in the end. Let's move on to example 3. In this problem, we're asked to solve for the amount of liters required to make 2 molar solution with 0.600 moles of solute. So remember the triangle to check our work later. You're going to need to cover up the liters and essentially divide moles of solute by molarity. We are going to be using, though, our dimensional analysis setup. So we're given 0.600 moles of solute, so that's what we start with. We want to get rid of the moles, so the moles must go at the bottom. Now, remember, since we're asked for liters of water, we get to use our molarity as our conversion factor. So 2.0 molar can be written as 2.0 moles per liter. Okay, so we can insert our conversion factor inverted. Okay, notice that it's the inverse. So that means the 2 moles go at the bottom, the 1 liter at the top. The moles, remember, can cancel, and then all that's left is to divide the 0.600 by 2 moles. And hopefully when you do that, you will see 0.30 liters of water as your answer. Let's take a look at example 4. What concentration of solution can be made with 50 grams of cobalt 2 chloride and 0.250 liters of water? So hopefully you can see that we're talking about concentration, which is synonymous with molarity. And this time we're given grams of our solute instead of moles. So our first step will be to convert grams to moles. So let's go ahead and set up our dimensional analysis to perform that calculation. You'll need your periodic table to calculate the molar mass of cobalt 2 chloride. Remember to round your masses to the nearest hundredth. Pause the video if you need to do that. Hopefully you got 129.83 grams of cobalt 2 chloride as your molar mass. Notice that you can cancel the grams of cobalt 2 chloride. Now that we've done that and we have moles, all that remains to calculate the concentration is to divide the moles by the number of liters of water. So let's bring in the 0.25 liters of water and perform that calculation. Hopefully you got 1.54 molar cobalt 2 chloride as your concentration for your solution. Now that we've completed the molarity calculations of these examples, let's take a look at how to produce a solution in the lab. So when making a solution, the first step is to determine the volume and the concentration of the solution that you'll need for your procedure. So what you want to do is use the molarity equation to calculate the moles of solute required. Once you have that, you'll need to change the moles to mass and follow the steps in the picture here. The first step would be to measure out the required mass of solute that you'll need. So in order to do that, you'll need to obtain an electronic balance and use a weighing boat or some other weighing container to place your solute in. So once you tare or zero your balance, you can place the weighing boat on top and add your solute. Once you've measured out the required mass, you can then add the solute carefully to a volumetric flask. Notice that there's already some water in the volumetric flask, and I know this is a volumetric flask because it has a line of calibration at the top here. So for example, if this was a 500 milliliter volumetric flask, once the flask has been filled to the calibration mark, we know that we have exactly 500 milliliters of solution in the flask. Also notice that there's a funnel in the mouth of the container. So the purpose of that is to prevent spilling of the solute as you're pouring it into the narrow-mouthed flask. After the solution or the solute has been added to the flask, you can then add a little bit of additional water, stopper the flask, and agitate or shake it to ensure that it mixes with the water. Afterward, you would carefully add water to the calibration line. So once you reach a point where it starts to get close to the calibration mark, you might want to use a dropper to add the water dropwise, or a plastic wash bottle to control the pouring of the water into the flask. And just like you would with a graduated cylinder or a burette, you would look very closely at the meniscus to make sure that you get an accurate volume. After you've made your solution, you can then label it with the concentration, with the name of the substance, the identity of the substance. So you could write the formula of the substance or the name of it, and then you would also include your initials and the date on which you made the solution. You could use it, put it out in the lab for use, or store it safely for use later. Let's look at another example of how you would determine the number of grams of solute needed to begin your solution. So how many grams of cobalt 2 chloride must be used to make 500 milliliters of a 1.50 molar solution? So once again, we'll start with our given volume. Notice how I'm always starting with a volume or a value in moles or grams instead of the molarity. The molarity is always going to be used as a value embedded in the dimensional analysis setup. It's because it's a conversion factor. So we're starting with 500 milliliters. Set up your T-chart, and you remember that the molarity equation is expressed in liters. So we'll actually be converting milliliters to liters as our first step, using the conversion factor 1,000 milliliters is equal to 1 liter. Notice you can cancel the milliliters out. These labels match. The next step, now that we have liters, is to use the molarity conversion factor to eliminate that label. So since we know we're getting rid of the liters will also be at the bottom of that conversion factor step. Okay, so the moles will go at the top. 1.50 molar is equivalent to 1.50 moles over 1 liter of cobalt 2 chloride. Okay, now that we have moles at the top, we're almost done. Because the question asks for grams, we know we only have one more step, and that's to change moles to grams. So you will need the molar mass of cobalt 2 chloride one more time here. Okay, so set up your conversion factor to change to grams and go ahead and solve. Multiply across, divide from the bottom. Notice again, the labels cancel diagonally. Hopefully you got 97.4 grams of cobalt 2 chloride as your answer for this problem. So that's how much solute you would need to add to half a liter of water to make the 1.50 molar solution. Next, we're going to take a look at some dilution calculations. First, let's look at what it means to dilute a substance. So the dilution is the process of adding water to achieve a lower concentration. In that process, the volume of the solution will increase. So notice how at the beginning in the stock solution before dilution, we have 6 particles present. When water is added and the solution is diluted, the number of particles stays the same, but the volume of the solution goes up. So that results in the concentration decreasing. Dilution can also be seen in this diagram here, with the stock solution being this dark blue color. Some of the stock solution is removed from the original container with a pipette and inserted into a new flask. When water is added to the new flask to dilute the concentration, you can see that the color of the second flask ends up lighter. So that is a nice visual indicator of a substance or a solution with a lower concentration. The equation for this relationship is M1V1 equals M2V2. So M1V1 represents the initial molarity and the initial volume, and usually that's used to represent the more concentrated, or the original stock solution. So in this case, it would be the darker flask. M2V2 represents the final molarity, or the final volume, or the result of the dilution. Let's look at some examples to see how we can apply this equation. In example 1, Alex adds 28.7 milliliters of sulfuric acid to a 1 liter volumetric flask to make 0.500 molar solution of diluted sulfuric acid. So you can see in this picture, we have a pipette, and what's happening is Alex is adding 28.7 milliliters of the stock to the flask. Now, one thing to note, since we're talking about sulfuric acid, when diluting a concentrated acid or base, the acid or base should be added to water. So there should already be some water present in this volumetric flask. And if the acid or base is very concentrated, then it should be added slowly, dropwise, to the water, because what will result is a highly exothermic reaction. So to prevent a violent reaction from occurring, it's important to proceed slowly. And another useful tip would be to immerse the receiving flask in an ice water bath to keep the solution cool. So back to the example. after the concentrated acid has been added to the flask, more water can then be added to create that diluted solution. And you can see in the end that a 1 liter solution of 0.5 molar sulfuric acid will be made. So we're looking for the original concentration of the acid, which in case of this equation is going to be M1. So when we're plugging in the variables, this is what the equation will look like. So in solving for M1 algebraically, we need to divide both sides by 28.7. So go ahead and plug that in. And upon solving, you should get a concentration of 17.4 molar sulfuric acid, the initial concentration of the solution. I want to point out something about this problem. Notice that the volumes given to you in the problem have different units. One is in milliliters, the other is in liters. So in the formula, it doesn't say liters, it says volume, V for volume. So what needs to happen is you need to make the units match. So whether you convert them both to liters or both to milliliters, it doesn't really matter. Although since we're talking about dilution, usually you'll be asked for a value in milliliters. So I would just convert them both to milliliters, but do what's convenient. So as long as your labels match, then you're good to go to solve the rest of the problem. But if one label is milliliters and the other label is in liters, then mathematically your problem will not work out correctly. Okay, so just make sure your labels match. Another thing to note is based on our original description of what dilution entails, what was mentioned was that the volume will go up, and you can see that we start off with 28.7 milliliters and we end up with 1,000 milliliters. So the volume did indeed go up. It was watered down. More water was added to dilute the solution and we end up with a larger volume. In addition to that, the concentration will go down. So our final concentration is 0.500 molar, but our initial concentration is 17.4. So the concentration does go down. Okay, so this matches with our description of what dilution is. And let's move on to example 2. So for example 2, Braden added 10 milliliters of 3 molar hydrochloric acid to a flask. So you can see here the pipette represents the addition of the concentrated acid to the flask. His lab partner accidentally poured in 60 milliliters of water. So here you could say his lab partner is accidentally adding 60 milliliters of water to the same flask and diluting the acid. So now what is the concentration of the acid? Okay, let's figure out what our variables are. So for our variables, we're going to plug in 3 molar and 10 milliliters for our initial values, since that's what we're starting with. For our final values, our molarity is the unknown. We don't know the concentration of the acid now. That's what we're trying to figure out. So that's what we're solving for, M2. 70 milliliters is our final volume. Okay, so where did the 70 come from? So if you notice in the problem, we're starting out with 10 milliliters of hydrochloric acid and we're adding, or the lab partner rather is adding 60 milliliters of water. So if you add those together, you will get 70 milliliters as your new volume. So that's the V2 that you're going to plug in. Okay, so it's important to pay attention to the wording of the problem to make sure you're plugging in the right numbers. Now we're going to solve for M2. So divide both sides by 70, and you should get 0.429 molar hydrochloric acid as your final concentration. Let's take a look at our values to make sure they make sense. So remember, the concentration was supposed to go down when it's diluted. So we went from 3 molar to 0.429 molar. So that makes sense. And the volume was supposed to go up. So we went from 10 milliliters to 70 milliliters. And yes, it went up. So that makes sense. You want to make sure that your answers are logical as you're moving through the problems. Next, let's take a look at example 3. Glacial acetic acid, okay, we talked about what that was in a previous slide, has a concentration of 17.4 molar. Okay, it's a very high concentration. Household white vinegar has an acetic acid concentration of 0.833 molar, so that's much lower. What volume of water will we need to add to 20 milliliters of glacial acetic acid to achieve the concentration of vinegar? So again, we are using the M1V1 equals M2V2 equation, and we're going to plug in our values. So the original concentration is 17.4 molar, and we're given 20 milliliters of glacial acetic acid to start with. Okay, our final volume is going to be 0.833 molar. That's the desired molarity. That is the molarity of the vinegar. And we're trying to figure out what volume of water we'll need. Okay, so we're trying to figure out V2 first. So we're going to go ahead and divide both sides by the concentration of vinegar to solve for V2. And that gives us our final volume of the solution. Okay, but this is not the answer. We're looking for the volume of water that needs to be added to the glacial acetic acid. The V2 is giving us the final volume of the solution. We're looking for how much water was added. So that will require some subtraction. So to figure out the amount of water, you need to subtract the final volume minus the initial volume, or V2 minus V1. So that's going to be 418 milliliters, which is V2, minus the initial volume, which was V1. And that will give us 398 milliliters, which is the volume of the added water. So that's our final answer. So we've completed our dilution examples. We're now going to move on to solution stoichiometry. So just like your typical stoichiometry problem, you want to make sure to always begin with a balanced equation. Because remember, in stoichiometry problems, we use the mole ratio, which involve the coefficients acquired from the balanced equation. We're also going to be using molarity as a conversion factor embedded in our dimensional analysis setup, because we're dealing with solutions. So let's look at our first example. How many grams of hydroiodic acid react with 0.108 liters of 0.500 molar calcium hydroxide solution? So acid and base, this is a neutralization reaction. So when you write your equation, hopefully you realize that in a neutralization reaction, your products are going to be a water and a salt. Okay? Once you balance the equation, hopefully you'll notice that the hydroiodic acid and the water get coefficients of 2. Now, to begin our dimensional analysis setup, we're going to start with the volume given to us, 0.108 liters. Okay? We need to get rid of the liters, so that should help you understand that you now need to incorporate the molarity value as your conversion factor. So remember, 0.500 molar calcium hydroxide is the same thing as 0.500 moles over liters. So we're going to insert our molarity conversion factor. Notice the liters will cancel. The next step is to eliminate the moles of calcium hydroxide. So this is where your mole ratio comes in. So you know moles of calcium hydroxide will go to the bottom of the dimensional analysis setup. And since we're looking for grams of hydroiodic acid, moles of hydroiodic acid will go at the top of our mole ratio. So take a moment and see if you can set up your mole ratio. Pause the video if you need to. Hopefully you got 2 moles over 1 mole for the mole ratio. Make sure your labels are correct. Now, because the question is asking for grams or mass of hydroiodic acid, we need to convert the moles of hydroiodic acid to grams. You will need your periodic table to determine the mass of hydroiodic acid. So go ahead and pause the video if you need to for that. Hopefully you got the 127.91 grams as your molar mass. Take a moment to notice that you can cancel out the liters here, the moles here, the moles of hydroiodic acid here. It's important to do that step to check your work to make sure you have the correct dimensional analysis set up so that you get your final answer correct. Okay, go ahead and perform the calculation on your calculator and see if you get the right answer. Hopefully you got 13.8 grams of hydroiodic acid as your answer. Let's move on to the next example. In example 2, we are going to use the same reaction, and we're going to be determining how many milliliters of 0.500 molar calcium hydroxide solution are needed to produce 50 grams of calcium iodide. So once again, stoichiometry problem. We're going to start with 50 grams of calcium iodide. Now, we need to convert grams to moles as our first step. So calculate the molar mass of calcium iodide. Pause the video if you need to do that. And hopefully you got 293.90 grams as your molar mass. The next step is to eliminate the moles of calcium iodide. So this should trigger you to set up your mole ratio. So the moles of calcium iodide will go at the bottom, and since we're looking for milliliters or an amount of calcium hydroxide, the moles of calcium hydroxide will go at the top. So hopefully you got 1/1 as your coefficients for the mole ratio. Make sure you have the right substances in the right spot, the right chemical compounds. Now that we've eliminated the calcium iodide, our next step is to determine the volume, milliliters, of 0.500 molar calcium hydroxide. So that should trigger you to use the molarity as the conversion factor here to get to liters. So because we're eliminating moles, you're going to use the inverted conversion factor for molarity to eliminate the moles. Okay, so it's going to be 0.500 moles at the bottom, 1 liter at the top. Now, because the question's asking for milliliters, we need to go one more step and use the conversion factor of 1 liter equals 1,000 milliliters to convert to our desired unit of milliliters. Take a moment to cancel out your labels, make sure they're set up correctly, and then solve using your calculator. Grams of calcium iodide cancel, moles of calcium iodide cancel, moles of calcium hydroxide cancel, liters of calcium hydroxide cancel. And hopefully upon using your calculator, you can see that the answer is 340 milliliters of calcium hydroxide. Now we're going to take a look at our final example. How many liters of 2 molar silver nitrate will react with 0.450 liters of 0.650 molar sodium chloride solution? So remember, we need to write our balanced equation. So we're given the 2 reactants here, silver nitrate and sodium chloride. This will be a double replacement reaction. And our products are silver chloride and sodium nitrate. So as it's written here, it's already balanced. So we have a 1-to-1 ratio for everything. We're going to start with our given volume, 0.450 liters. Now, since we're given liters, we need to go ahead and incorporate our molarity conversion factor for sodium chloride to obtain the moles of sodium chloride. So go ahead and put 0.650 moles up at the top and 1 liter at the bottom. We're setting it up this way so that we can cancel out the liters. Now that we have moles of sodium chloride, we need to eliminate the moles by using the mole ratio. So we are going to then input moles of sodium chloride at the bottom, and the other part of our mole ratio will be moles of silver nitrate, the other compound mentioned in the problem. Okay, so hopefully you got the correct mole ratio. And next, we're going to eliminate moles of silver nitrate using the molarity of silver nitrate as our conversion factor. We're asked for liters, so we know that that will be our final step. So this time we're using the inverted conversion factor for molarity to eliminate the moles of silver nitrate. Go ahead and use your calculator to solve. Hopefully you got 0.146 liters of silver nitrate as your answer. Now you should be ready to complete the practice problems on your own.